We now discuss the solution of a problem from the section Group Theory that has appeared in the TS Set 2019 examination. The question is related to the first Sylow's theorem, and this question is relevant for the aspirants of JL, junior lecturers, degree lecturers, TS Set, AP Set, CSIR net examinations also. We first review the first Sylow's theorem. What is first Sylow's theorem? Recall first Sylow's theorem as it is given in the textbook, a first course in abstract algebra by J.B. Fraley, 7th edition, 2003. And in this book, it is given as theorem 36.8, and the theorem and the first Sylow's theorem stated in this book is: let G be a finite group and let order of G is equal to p power n into m, where n greater than or equal to 1 and p is a prime and p does not divide m. It amounts to say that p power n divides order of G and p power n plus 1 does not divide order of G. Then the first part, which is ticked here, is the first Sylow's theorem in all textbooks. That is, G contains a subgroup of order p power I for each I where 1 less than or equal to I less than or equal to n. For each I, 1 less than or equal to I less than or equal to n, G has a subgroup of order p power I. This appears in all the books. Agreed. The second part, what we have written here in color, appears in this book only, and I have not seen this result in other textbooks. It might be there as an example. Now the second result, what under first Sylow's theorem, is every subgroup H of G of order p power I is a normal subgroup of a subgroup of order p power I plus 1 for 1 less than or equal to I less than n. Now by the first part, H, there is a subgroup H of order p power I, and there is also a subgroup of order p power I plus 1 for this I, 1 less than or equal to I less than n, I less than n, I less than n. And this says every subgroup H of G of order p power I is a normal subgroup of a subgroup of order p to the power of I plus 1 for 1 less than or equal to I less than n. The second part is very important. Agreed. Now, using that theorem, we have a very important result. That result is no group of order p power r for r greater than 1 is simple, where p is a prime. It is a important result, and it will help you in many ways in your examinations. So it says no group of order p power r for r greater than 1 is simple, where p is a prime. The proof is very simple. You can also see here. Let G be a group and whose order is p power r, where r greater than 1, r greater than 1, r greater than 1, there is a stress r greater than 1, where p is a prime. Now, by the first part of the above theorem 36.8, namely the first Sylow's theorem, G contains a subgroup H of order p to the power of r minus 1. So by the first part of the theorem. And we will use the second part. H is second part, H is normal in a subgroup K of order p to the power of r minus 1 plus 1. Use the second part, that is p power r. Now who is the subgroup of order p power r in G? It is G itself. So that means K is equal to G. So G, by first part, G contains a subgroup H of order p to the power of r minus 1, and by second part, that subgroup H is normal in a subgroup K of order p to the power of r. P to the power of r is p to the power of r minus 1 plus 1. And the subgroup of order p to the power of r of G is none other than G only. Therefore, K is equal to G. Thus, H is a normal subgroup of G. Normal subgroup of G. So, thus, G has a non-trivial normal subgroup H of order p to the power of r minus 1. Because r is greater than 1, that is why it is non-trivial. It is non-trivial. Agreed. So this is also a very important byproduct. That means if you have a group of order p to the power of r, then it has a normal subgroup H of order p to the power of r minus 1. This result is also very important. You can use it in your arguments. Agreed. When G has a non-trivial normal subgroup H of order p to the power of r minus 1, G is no longer simple. Because what is simplicity of G? It has no non-trivial normal subgroups, but it has non-trivial normal subgroup H of order p to the power of r minus 1. Therefore, G is not simple. So it says whenever G is of order p to the power of r, where r greater than 1, p is prime, is not at all simple. That means no group of order p to the power of r for r greater than 1 is simple, where p is prime. And using this result, you can also say, example, a group of order 2 to the power of 4 is equal to 16 is not simple. P is 2, R is 4. You apply the above result, it is not simple. And further, you can use this important byproduct. It has a normal subgroup of order 2 cube, that is 2 to the power of 4 minus 1. 2 cube is equal to 8. Further, you can also have a group of order 3 cube, that is equal to 27, is not simple. And it has a normal subgroup of order 3 square is equal to 9, using the above arguments. So, sir, why are you teaching all these things? It's because of this example. And there is one example that appeared in the TS Set 2019 mathematics examination. What is that result? That result is that question is question number 69 with this question ID, and the question is the number of simple groups of order 27 is. The question asks how many simple groups of order 27 are there. You are given 4 options. These are the 4 options given to you. Agreed. Now let's argue. Solution. Recall. Just now we have proved no group of order p to the power of r for r greater than 1 is simple where p is a prime. So now, therefore, no group of order 3 cube is equal to 27 is simple. So, p is 3, r is 3, and r greater than 1 it is. So, no group of order 3 cube, that is 27, is simple. That means every group of order 27, that is 3 cube, is not simple. That means there are no simple groups of order 27 at all. Therefore, the number of simple groups of order 27 is 0. There are no simple groups of order 27 means there are 0 number of simple groups of order 27. So, our answer to this question is option 3, where in option 3 we are given 0. So, that is the detailed discussion of the solution of the problem that appeared in the TS Set 2019 examination. Agreed. But there is an alternate method of attacking this question. So, what is that? We are going to talk about that in the next slide. So, we talk about alternate method. For this alternate method, we state this lemma. The lemma is lemma 2.9.1 from the textbook Topics in Algebra by Ian Herstein, which is a most famous textbook and one of the best books for all competitive examinations. If this theorem lemma says if G is a finite group and H not equal to G is a subgroup of G, that is H is a proper subgroup of G such that the order of G does not divide the factorial of the index of H. That means order of G does not divide the index of H factorial. Then if this is the hypothesis, then H must contain a non-trivial normal subgroup of G. So the lemma asserts H must contain, so that means H will have a non-trivial normal subgroup of G, and thereby G cannot be simple. G cannot be simple. And for this result, you can see the textbook Topics in Algebra by Ian Herstein at page 73. You can also see this in the other textbook, and this lemma appears as index theorem. The name is given for this, the index theorem, in Contemporary Abstract Algebra by Joseph A. Gallian at page 426. Both these books are very good books, standard textbooks, and for all examinations these two textbooks are recommended. So this result you can use now for this example. And I thank my student Sripad Venkatesh, and who is working at CVR College of Engineering, for bringing this result to my notice. Thank you, Sripad Venkatesh. Agreed. Now we attack our question. Question number 69 with this ID. The question is number of simple groups of order 27. Options are here. So we have order of G is equal to 27, that is equal to 3 cube. By Sylow's first theorem, G has a subgroup H of order 3 square, that is equal to 9. Agreed. We agree. And now the index of H in G, the formula is when G is a finite group, order of G by order of H. Order of G is 27, by order of H is 9, that is equal to 3. Then in that case, the order of G does not divide the factorial of the index of H. How? Order of G is 27. The index of H is 3. Its factorial is 6. So 27 does not divide 6. So this condition is satisfied. Then use this lemma 2.9.1 or index theorem. You'll have H must, so this H must contain a non-trivial normal subgroup of G, and in this case H itself, and thereby G cannot be simple. So by the above lemma, G is not simple. G is not simple. So that means this says no group of order 27 is simple by this argument. Therefore, the number of simple groups of order 27 is 0. Therefore, the answer is option 3. Option 3. I also add one more note here. The note is, using the above lemma, this lemma 2.9.1, which are the index theorem, we can prove that result. No group of order p to the power of r for r greater than 1 is simple where p is prime. How do you do that? It is simply wherever there is a p power r, wherever there is a 3 cube, for p it is 3, for power 3r. And same argument you repeat, then you will get the proof of this result. So this result by itself is very important. So that is the detailed discussion of the solution of the problem that appeared in the TS set examination from the group theory, and I am sure that you have understood the theorems, the results that I have used, the arguments that I have put forth, and the solution for this question. I am sure that you have understood all these things, and I wish you all the best. Thank you.